um, I've put several unedited video clips up on Feral, which is actually a recording of what we've done and what we've spoken about and so on. So okay, so both recordings are running at the moment, and so I'm going to start off by talking about UML. So UML stands for, guess what? It stands for Universal Modeling Language. And it's this little talk is going to be a little bit boring because I've got quite a lot of detail to give you. But think of it, think of the end purpose of UML. It gives you tools for representing a model in an object oriented fashion. Okay, so the key thing to note at the moment is that UML is very object oriented. It's assuming that you are looking at the universe in object oriented terms. In other words, there's nothing in the universe, in the real universe out there, that's not an object or properties of objects. There's nothing else. And I mean, it's quite a long time ago since we had a bit of a discussion about what an object is, and I asked you what I thought were tricky questions, like, is a flash of lightning an object? I mean, usually you think of objects as things that you can name and things that persist through time and things that have properties and things that have a geographical location. But does a flash of lightning, does that count as an object? Uh, or does a squeaky noise that you hear, is that an object or is that a property of something else? Well, it's likely to be a property of something else. But as far as flashes of lightning are concerned, I don't know. You might ask yourself the question, well, what about your thoughts? Do they count as objects? I mean, you have thoughts, they're as real as anything can be, but do they have all the properties of objects? Do they persist in time? Well, no, they don't. They're very transient, they're very quick. Can you name thoughts? Well, no, not really. And one test of something being an object is that you have a criterion of identity. I mean, let me just write this for you have a criterion of identity. In other words, given two possible objects, uh, do you have a rigorous test for whether or not one of those objects is the same as the other? So the idea of objects having an identity and an accessible entity is quite important. Anyway, think about that because I find it quite, it's a bit philosophical, but they're quite interesting questions and they're important questions. I mean, you can think of in science, whether or not particular particles are genuine objects or are they just logical fictions that help to explain the physical world, or I don't know. There's a lot of things. There's a lot of entities in physics that you could ask the question: well, are these genuine objects, or are they just artifacts, logical fictions that are needed to explain uh, behaviour of the physical world? Anyway, I'll leave you to think about that. But we could always come back to that. And we're going to discuss Occam's Razor. Okay, so we're going to do that. Anything else? So we're going to next week probably is look at the most advanced topic in the course, and that's threads. And if you were doing the course last term, I did talk about threads. I did talk about concurrency. and I defined concurrency as the apparent parallel execution of threads. And we learned from the work that we did on computer architecture that a computer can only ever execute one single instruction per unit of time. And the question arises, well, how does a computer create the illusion that it's doing lots of things at the same time? You know, that it's not only lowering the aircraft's wheel and measuring and analysing the fuel situation and monitoring its position in the sky, and so on and so on and so on. How does that happen by means of um, how does that apparent illusion of things being done in parallel occur? Well, we looked at one main way, and that is simply that you can execute, say, three programs. Let's think about programs. By first of all running a few instructions of the first program, stopping everything, then loading the CPU with a second instructions, a few instructions, maybe 100, few instructions from the second program, running those, and then faster than the eye can see or the mind can understand, you now start executing instructions from the third program. And and I think somebody asked me, well, about the meaning of interleaving. I mean, it's a bit like taking two um, half packs of a single deck of cards and interleaving them. You're just making the two packs into one pack by just flicking various cards into final position. I mean, I can't actually demonstrate that obviously but I think you know what I mean. Anyway, and so it's probably next week we're going to talk about inheritance. Going to remind you about what classes are, what subclasses are, what superclasses are, what abstract methods amount to, and what interfaces actually represent. So I'm going. I mean, it's quite easy stuff, but it's a little bit of terminology. A thread can be defined simply as a single sequence of instructions that can be executed independently of any other thread. So having three threads simply means you've got three sequences of instructions. And the question is, well, how do you actually execute those three sequences? Well, technically and logically, I could execute one instruction from one, then execute the first instruction from the next, and so on. And that's called interleaving the execution of those programs. But anyway, that'll be a topic for next week. And what I'm going to do is to upload the document on UML. There's 3 documents in total, and I've got to try and get the order right. So and I've no idea. I've got 3 documents, and I'm not quite sure which order they're supposed to be. I think it's probably going to be. I'll try this. I might have to backtrack. I might have to test your patience a bit. So, are there any questions about what we're doing? So this is. Let me make this bigger. This is. Okay. It's an overview. No, it's not. So this. Let me start again. Um, this is an overview of object-oriented analysis. So that's not what I want. So I'm just going to get rid of that and try. Oh, this is going to take ages, won't it? I'm going to try uploading another presentation. So let me, so I think it's going to be this one. Okay, so I'll kick off with this. This is an overview, but it's a fairly detailed overview. And I'm starting by talking about general things. And the first question I want to consider is this: it's the importance of modelling. And the intended session outcome, so for this part of today's work, is for you to come to understand and recognize the need for abstraction in modelling and the incredible importance of abstraction. And I want you to understand the context in which UML, so this is a language, was developed. It's a language consisting of symbols, and I think that's probably the best way of describing the modelling language. So the first thing I want to ask you, excuse me, is well, what's meant by a model? And I could give examples of models because I can give you an example of a model of a real train. I could show you a toy train, and this is, to all intents and purposes, captures some of the essential characteristics of a real train. It's got wheels, maybe it's got an electric motor, or if you're quite wealthy, maybe it's got a steam component. It's a model of a steam engine, and it's actually got a steam generating cylinder on board. And you can model molecular change during short periods of time. Well, you can actually demonstrate what happens when a molecule actually changes, it reconfigures during a short period of time. I'm not a chemist, so I can't say very much about that. Maybe you've all heard of, I'm sure you have, the Big Bang, as in the Big Bang theory of the origins of the universe. What happened and how did it happen? Show me pictorially or in any other way what happened when the Big Bang occurred. Well, interesting. I mean, did it take no time at all to happen? Did it take a long time? Did it take an infinite amount of time? Is it still happening? Are we, there's lots of questions. There's just south of where King Henry VIII used to live. There's a place called Kew, and there's Kew Gardens. It's a wonderful area. Whichever you go to London, do have a walk round Kew Gardens. It's exquisite, and there's some quite useful scientific work being done in Kew Garden in terms of, well, I think it contains, somewhere in Kew Garden there is a repository of every seed known to man for various species of plants and flowers. Okay, what about a model of a lift system with, or maybe make it more complicated, with a distributed control? Could you create a meaningful model of a lift system? And you might say, well, why? Why are you asking us this? Well, I'm asking you this that I think to create a model of a system that you want being built will help you enormously in the task of actually building it, and especially if it's a software system that you want to model its functionality and what it does. So how about this? A model is simply, if I can use that word, simply a simplification of reality. And if you're simplifying reality, um, does the fact that you're simplifying something involve abstraction? In other words, and by abstraction, I mean you're avoiding giving unnecessary details. So I'm asking you to think about what you understand by the term abstraction. I want you to think about that. Well, a model arguably is a set of blueprints that would enable you to create a system. I mean, maybe you know about architects' blueprints or blueprints for the design of a mechanical part. What a blueprint gives you is the essential character of a system. No detail, just the bare bones. And you could ask, well, how detailed should a blueprint be? I mean, if I were to ask you to draw right now a blueprint of the room that you're actually working in right now, what would it look like? How much detail would you specify? Would you actually give me details of sizes and lengths of walls, or if you've got windows, would you put that in? And a more sophisticated definition of a model is this: it's a semantically closed abstraction of the system. I think what that means is that it's a way of actually specifying a system for which you don't need anything else to understand it. It gives you the key, and other things being key definitions of all the terms used and all the features in perhaps a drawing, what the meaning of this particular dotted line is, and so on. I think that's what's meant by a semantically closed abstraction. But it's an abstraction. It's you're getting rid of all unnecessary detail. So the question is why? Well, I'm going to start again. I was going to say, why do we make models? But a better question would be, why should we make models before attempting to build something? I mean, it's like, why should we plan the construction of a system before building it? Well, one reason for making models is to communicate the structure and behavior of a software system to the people around us, to the people who are going to be given the task of making the system or programming the system. I mean, but this also holds, it's so general. It also holds for, you want a new garden? You should plan the garden. You should model it. Okay, you've got this extraordinary idea of having a garden built on 5 different levels, and and in a particular way. The best way to communicate what you want to build is to show a team of gardeners or landscape engineers your model, and at a glance they can come to understand what it is that you want. So second reason is to actually visualize and exercise some control over a system's architecture. What I mean by that is simply, well, supposing I'm building a complicated thing. Maybe it's an operating system to run on a Dyson vacuum cleaner. What I can do is to show you the parts of this complex whole and show you their relationships, the parts' relationships to one another, And that enables me to have some control over the system's architecture, because I might spot an obvious fault, or maybe I might spot the fact that there is no need to have part X in the system. It's not playing a useful role, or it could be modified. So a model can assist in understanding a system under development. In other words, to enable us to reason about and to analyze a system. I mean, I think I've spoken to you about the complexity of software systems such as Windows 10, and I think I've claimed that there's no one person that understands the entire software system as a whole. But you can model it, you can present a model of what happens to enable people to overall understand the operation and structure of the system. Uh, so the other thing is that you can expose opportunities for simplifying the system. I mean, you might think, oh, Kinberg, you've made this very complicated model, but surely you could make it simpler by doing this, that, and the other. And maybe you can, instead of having 6 different flights of steps, can't you just make do with one? Right. Um, anyway, I'm going to skip the risk uh, heading there, but I'm going to talk about a little bit about the uh, the purpose of documenting and recording decisions during the design and implementation of a complex system. It's very important to say why you've actually made a decision to include this or that particular feature, or it's very important to record the reason why you've actually chosen to make this or that decision. And you could think in terms of like gardening terms. Why on earth did you make a decision to use steel for your steps as opposed to brick, or as opposed to uh, slate? Why? Why? So if you think about it, it's important to document what you've done. Otherwise, if you resign from your job and you're the only person who knows why certain decisions were made, but you haven't written them down, you're going to leave a nightmare situation for the person replacing you. So in building architecture, real architecture, 2 important sets of documents for building design are what are called the drawings, and secondly, the specification. And the drawings consist of a wide variety of graphical devices. In other words, pictorial, graphical uh, documents. For example, the architect might have the front elevations of a building, what the building looks like from the front. Might have floor plans, what the internal structure of a floor is. What are called detailed drawings. So, for example, the architecture might actually show you exactly how the I'm sorry, there was just a slight interruption there. Might actually show you how a particular uh, joint of the upper floor occurs with respect to the supporting walls, and be given in detail. And the architecture might provide a site map, like whereabouts on the land is the house to be built, how does it all fit into the environment, and so on and so on and so on. I mean, quite a lot. But the point of all these drawings and specifications He might specify the materials to be used because he's calculated um, the load capabilities of walls and so on. Actually would enable anyone to come along and to construct the building. There's enough essential information to build the building. And the same is true in software. Okay, so I'm going to just keep on a little bit at the moment. What ordinary cases of modelling come to mind? I mean, drawing a line as shown, um, you know, let me see if I've got, just going to, um, let me see, I'm just going to go back to my little drawing device. I mean, here I go, look, let me, let me use a pencil instead. I'm going to show you a model. There it is. It's a straight line. I'm modelling the wall in my back garden. So I can actually, give you a length L. I can actually give you a width. I mean, a straight line. That is simplifying something in the real world. It's a model of my wall. And I'm modelling another wall. I don't know whether you can see that. And I've actually modelled a gap. I've also modelled a gap. Can you see that? No. I mean, let me just. I'm being inundated with. Um, no, it's not working. We're doing it. So this is my second wall. This is my original wall. And what I've actually put a ring around is a gap in the wall. And I'm modelling that by showing you this gap. I mean, at the moment, there's actually an old wooden door in the corner. And I'm modelling that. And I could use this model to show a gardener or some kind of uh, uh, garden engineer what to do because I want to get rid of it. Okay, so I, I'm being. You might think I'm being a bit silly because I'm talking about some things, but the idea of abstraction comes to one thing, and that is the removal of all unnecessary detail. And you can even use abstraction in mathematics. Like I could let the what I'm in fact is a variable a represent any number in maths. I'm abstracting from all numbers. I'm using a symbol a to represent any possible number. Have you modelled anything recently? Does planning a journey from one side of the room to the other involve modelling? Maybe. If you had to build an android or some kind of robotic device to perform the task, you would probably need to get the device modelling to enable it to model a path between 2 points A and B. And anyway, all this is to do with Occam's Razor, what's called Occam's Razor. And it's sometimes spelt uh, this way, Ockham. But Occam was a logician, not a magician, somebody who specialised in logic in the Middle Ages. And he's very famous for saying one thing, and it's this. So listen carefully, because I'm not going to write it down. In Latin, he said this: do not, whatever you do, do not multiply entities beyond necessity. In other words, don't have any baggage, don't have any unnecessary detail. And the analogy is that if you're going to climb Mount Everest, don't take 6 suitcases. You won't need them. Completely unnecessary. Just take the necessary essentials if you're performing some particular task. And Ludwig Wittgenstein, very famous philosopher, became nearly famous nearly 100 years ago for proposing that sentences of language are in fact models of reality, and model sentences actually model reality. And he's also famous for inventing truth tables, which I think you have certainly come across in my course. So, okay, what is the practical importance of modelling? Well, modelling is, listen for this, listen to this. It's a proven and accepted engineering technique. It's taken very, very seriously out there in the real world of people making big systems, making roads, making airports, designing airplanes, designing space vehicles, and modelling uses a divide and conquer principle. And what I mean by that is that um, you are going to simplify the problem by not only removing detail but um, breaking the problem of what you're designing into parts. So you're reducing the task of building a big system into a lot of little systems. You're breaking the problem down into parts. And the fact of the matter is that we build models of complex systems because we cannot understand such a system in its entirety. We cannot survey the operating system of Microsoft 10, or sorry, Windows 10, which has got hundreds of thousands of quite difficult lines of program code. And building a model enables us to build the right software correctly. So that's quite an important thing to say. It helps us to build the right software correctly. It's not going to help us to build the right software, but it's going to enable us to do it correctly. So you might want to think about the comparison of modelling approaches in software. Well, one is functional approach. In other words, okay, I've got a brilliant idea for I don't know, for let me see, computing the likelihood of such and so events happening at a particular time, and I can do that algorithmically. I've got an understanding of what the program looks like, and I've got an idea of what functions or procedures I need, and I go ahead and just write it all down. Right? But such a non-structured approach is going to yield a system that's brittle because you can actually break it easily by changing parts of it. And the second approach, general approach, is object-oriented. And as building blocks, you use objects, classes, and the objects that you're going to use are drawn from the vocabulary of the problem space. So, for example, if I'm designing a lift system, I'm going to use as objects things like lift doors, lift buttons, lifts themselves, lift controllers. And they're all things that belong to the actual space within which I'm going to design a lift system. Models are very important in all engineering disciplines. When something's to be built, drawings are made that describe or depict the look and behaviour of the thing. And it might be a new Dyson vacuum cleaner, it might be a nano device, or it could be, I've mentioned motes on one or two occasions, a mote, M-O-T-E. Here is a little example of a mote, and it consists of a little processor unit and some radio frequency communications and a little bit of memory and so on and so on, and maybe a solar panel to keep it energized. And it's tiny, and I'm afraid I can't remember I think this line here is helping me to understand this model. This line, as I think, is 1 millimeter long. So it's just about 10 by 15 millimeters. And because you produce them in their thousands, I can produce them very cheaply, and I can use them for such things ranging from military use, because this little guy has got a motion detector, and maybe I can scatter them in a field, and when incoming soldiers enter the region, these are going to alert by means of a network of communications, alert some kind of central base station that there's movement in the area. Or, the sensor might be not a motion detector, but a fire detector, a temperature detector. So a device like this, which is tiny, and there's thousands of them scattered over a particular forest somewhere in the world, they can alert the forest fire brigade that there is a fire has actually broken out in a particular geographical sector, because not only does it have a temperature sensor, it also has something like a GSP that knows where on the Earth's surface it is. But the point is that I can actually design a mode in an object-oriented way. Look, here's a particular functional device. Here's another one. Here's another one. Here's another one. And the model is actually going to show me these parts. So I've broken the overall system down into parts, and I can actually create the model from which this device was actually built. So I haven't shown you this before, but that is the mote. That blue little object is the mote placed on an American. I think it's a dime, I think. It's tiny. And I probably got the dimensions wrong, because that, in relationship to a dime, is not 1 millimeter. It's probably a tenth of a millimeter or something along those lines. So during the work of making a model engineers need to investigate the requirements of the finished product, such as the functionality, the appearance, the performance, and reliability of the thing. And they must create a model that describes all the different aspects of the product. It's not just size, it's not just materials, it's not just the electronics or the particular software, it's not the particular CPU that's being used, it's cost and ability to survive in its natural environment. There are a lot of different factors to be considered, and the model therefore is broken down into what are called views. So this is an object, this is a UML term, views, and a view is is used to describe a specific aspect of the system under construction. And remember one thing, uh, if you're creating a model, it is creative work, and there's no final solution. I mean, don't expect there to be a final solution to a task that Chris Kernberg has asked you to make. There's no finished solution, no correct answer. It's checked at the end. So remember that. It's like a computer scientist or programmer is a bit like an artist when it comes to creating a software system. There's no end to the process of improvement of a system. So a picture or a pictorial model, because it's models that we're talking about, is, as you will recall, worth 1,000 words. And a picture doesn't have to be graphical. It can be a logical picture. Right? You can think once more about Wittgenstein's picture theory of meaning, namely the meaning of a sentence somehow is a logical picture of the reality it's describing. All right. So, but the take-home message here is that pictures, diagrams, graphics is is worth an incredible amount. It's very, very useful for all sorts of the purposes that I've mentioned, like to understand the overall system, to check the construction of a system. You might see that there's something unnecessary or something wrong in the picture. So I apologise for that. The useful criterion of judging the quality of models, if that's what you're interested in, is first of all, it's accurate, correctly describes the system that you want to be built. It's consistent, in other words, the materials from which it's made and its survivability in the environment and its size and its cost are all consistent. Right? A useful model is going to easily communicate the product that you want to make. And a useful model is one that you can change very easily. If you do, for example, if you detect some kind of fault in the presence of a particular component, you can change it. And maybe you can change all the others as well, equally easily. And usefulness is that a model is easily understood. In other words, you can use it. It's usable. Easily understood means it's usable. Even Chris Kinberg can understand it. Even Chris Kinberg can use the model if I'm being asked to create the device. So, so the purpose of what I'm about to talk about now is to give you a bird's eye view of the overall UML system. And an intended outcome here is that you will appreciate the fact that the role of a designer will develop several views of the product and construction. And one such view is what's called the use case view. Okay, this is important, the use case view. I mean, whenever you talk about UML, you're bound to talk about use cases. So I'm going to explain what a use case is. And I want you to familiarize yourself with some of the key UML terminology. So So first of all, excuse me again, um, UML is going to model systems using purely OO concepts, object-oriented concepts. In other words, concepts relating to objects. And we can, secondly, move from a conceptual model of a system to executable parts of system that will actually finally implement the system. And um, I don't quite, I can't quite remember why I put here address issues of scale. Well, certainly we can talk about scale, but why shouldn't we be able to talk about scale? But finally, you can create a modeling language that's actually usable by both humans and machines. I mean, this is the fascinating thing about UML. If you give a specification in UML, then not only can Chris Kimberg and others use the model, do something useful with it, like build a system, but it could be understood by machines or robots, and robots and machines can actually then go on to construct the specification given by the UML model. Okay, so no single method or design process is implied by the language itself. A modeling language, because it is a language, simply gives us the symbols and rules for their use that enables models to be constructed, as we'll see. And everything in UML is based on OO, okay? And just out of factual, as a matter of fact, UML can be used to model a broad range of systems, such as information systems, embedded real-time systems, distributed systems, technical systems, system software, business systems, like accounting systems, whatever you name it, it can do it. That's all there is. The world, I've been saying all along, that there is this view that the world consists of nothing other than objects, and every system or subsystem in the world, in the universe, is an object. And therefore you can actually represent anything happening in the world, or anything you want to happen, by means of objects and their relationships. Right. So this is important. So we're talking about developing a system here. So there were 5 phases. 5 phases. You can always distinguish 5 phases. And if you look at a system that's just been built, you can turn around and say, well, phase 4 wasn't done very well, or phase 5 was actually not done at all well, or even phase 1 was a very bad, very badly done. So the first thing is this, right? You need to know what the system's needed to do. What is it required to do? Give me an analysis. Give me a comprehensive analysis of what the system is supposed to be doing. What do you want it to do? Right. So to help represent the result of analysing the set of requirements that you want the system to do, you use use cases to capture the requirements. So in use case modelling, people who will interact with the system are modelled together with the functionality required from the system, which makes up the use cases. What do you want the system to do? Look, I've got a system in front of me. How can I interact with it? What exactly do you want the user of the system to get from it? All right. Sorry about that. There's an incoming call. Um, okay. Um, in use case modeling, agents or actors who will interact with the system are modeled together with the functionality required from the system. And we're going to see an example of a use case, and I hope you're not going to be disappointed with it. It's so simple. It looks like kid stuff. So the so the actors or agents, like you and me, the human participants, and the actual use cases are going to be modelled using use case diagrams. So these include relationships and communication associations with each other. So each use case will, in addition to being presented with a diagram, will also be described in words. Right? So let's get that out of the way. Step one, user requirements. In UML, you provide a set of use cases, which we haven't seen yet, but we will do. Second step is analysis. Alright, the analysis of the system. This phase involves the primary abstractions. In other words, what classes and objects do you need to have in order to start thinking about the construction of a system? So in this stage of analysis, classes that model um, um, the primary abstractions, things like going back to the lift system, things like lift buttons that you press, or a lift controller, or lift doors, and so on. So how at the second stage analysis, you're going to give those classes that model the primary abstraction. The primary abstraction in a lift system is going to be things like buttons, along with their relationships to one another. And these are going to form a class diagram. Okay, so the second stage, which is the analysis phase, is going to result in a class diagram, a UML class diagram. And once we've got the classes as a sort of step 2B, right, it's a part of the second step, you can discuss and identify collaboration between the classes to perform the use case functionality. And okay, so let me just read ahead. So what we can do, okay, if we've got the classes that we need to actually build a system, then we can talk about a further understanding of the dynamic nature of some of the modules and the way in which they can communicate with other objects. I mean, that might seem tricky, but you'll get a good understand. Right. So okay. So in the analysis phase, we're going to defer any detail. We're not going to consider detail. We're just looking at things in a very abstract way. Right? So I think this is the third step, and the third stage is design. The results of the analysis phase are going to be expanded or translated into an actual technical solution. And if we need to, we're going to add a few new classes in order, and we're doing this in order to actually move towards a solution in software. So all this results in a detailed specification for the construction and implementation phase. So the next stage is really the implementation stage. We've got what we need to fire away and to build a system. And we've actually got to decide whether or not we're going to use well, we're going to use programming, but are we going to do that in hardware or software or both? A combination of the two is entirely possible. You could go do everything in hardware if you wanted to, everything in software, or a combination of the two. So I hope that surprises you a little bit. All right. So what we're thinking about doing is to write some OO program, maybe using some object-oriented programming language such as Java. Right. So the last stage, and it's incredibly important, is the test phase. And a system's going to be normally put through its paces by means of what are called unit tests and integration tests and acceptance tests. Now, okay, a unit test is that you're going to test, you're going to take a block of the system out of which, the system's going to be made out of chunks and blocks of software, like software classes and objects. You individually test those to make sure they're working correctly. And an integration test is where you're actually testing all the units joined together as a whole. Right? And finally, an acceptance test is this. And it's just answering the question, does the system actually do what the original designer or the client actually wants it to do? In other words, something like, does the lift system actually work according to what the requirements were at the time? And the acceptance tests are actually conducted by the customer to verify that the system satisfies the requirements. And it's similar to a system test. And I guess the different test teams will use different UML diagrams as the basis for their work. So, for example, the unit test uses use case diagrams, integration tests uses component and collaboration diagrams, and system tests implement use case diagrams to validate that the system behaves as initially defined in those diagrams. So what am I saying here? I'm saying that use case diagrams are going to be used for the testing of the system. Why? Well, we started off by generating some use case diagrams that actually state clearly and unambiguously what the system's got to do, what we want the system to do. Okay, so just pause for a moment and hope that you're not finding all this too tedious, but it's quite important. So we've seen that UML can be used for a range of modelling tasks. In other words, all the phases of development. So let me just go back. All the phases of development for all types of systems, and the general modelling of constructions that have both a static structure and a dynamic behaviour. All right, so my question is, should I talk about views? Because I recall this is quite a boring session, and I'm just going to show you this diagram, which shows and identifies the different kinds of views, perspectives on the system. So there's a concurrency view. What do you want the system to do in parallel, as it were? How do you see the system being deployed? What are the components of the system? And what's the use case view? And I put the use case view in central position because it drives all the other views ultimately. Alright, so I'm going to say in this section 1.1, I'm going to talk a little bit about the use case view. The use case view shows the functionality of the system, as perceived by users of the system. Right? The logical view shows how the functionality is designed inside the system. As we've seen, it's going to be based on the classes and the objects being used in the system. And component views shows how all the code components are organized. And the concurrency view shows the concurrency within the system, communications and synchronization. And I think I've got a little example to show you of that this afternoon. So I'm just tending to skip through this now a little bit. Yeah, I'm going to leave you to read this if you're interested. Um, and I'm going to now talk about diagrams. These are the graphics that show model elements and symbols arranged to show a particular part or aspect of the system. So a diagram, you will see, is always part of a specific view. You know, the views that I've mentioned already. So let's turn our attention to use case diagrams. A use case diagram defines what a system does without specifying how it does it. It specifies the desired behaviour, and it promotes communication between experts in the area and users of the intended system. So use case diagrams. Here is a silly little example of a use case system. So a use case system could be used by architects and developers and information modelers. So this little circle is going to represent a particular use, and I'm connecting that to an actor or an agent that uses the system. So this is a little very simple, idiot simple example of a use case. It's showing a person who interacts with the system, and this is designed to represent the way in which the user does actually interact. What does he do? What can he or she do? So a use case diagram represents a set of functional requirements on the system. It represents the achievement of a tangible amount of work by the system, and it also provides a starting point for testing the eventual system that's being built. So here's a good definition of a use case. Right? It's a description of a set of sequences of actions that a system performs to yield an observable result of value to a person or a user. I think that's a pretty good working definition. And where are we now? Okay, here we go. Okay, so a class in UML is a description of a set of objects that share the same attributes, operations, relationships, and semantics. So I could use a rectangle to represent a class in UML, and I give it a name. So I'm going to give it a random name, a window, and I suppose I'm representing maybe a window I can see on my screen or something like that. Its properties or attributes is going to be the place of where the window is, in other words its origin, and the size of the window. I mean, I could actually specify that it's going to be 10 by 5, and the origin, the place, the location of the window might be at x, comma y. And I've got two operations specified on the window. Let's open the window, close the window. And I can show by means of a class diagram. So that's a class. This is a class diagram. I've got a portfolio class, which is related to an instrument. I think it's a financial instrument. And I'm expressing a relationship between a customer and a portfolio of, say, shares or stocks and shares. So a customer and the relationship he has with the portfolio is that he owns it. And there's a second object called a trader, which handles and manages the portfolio. And the portfolio involves, amongst other things, what's called an instrument. I don't know what an instrument is, but so this is a class diagram. It's showing four classes and their relationships. I don't know what this is. It's probably part of the diagram above. Okay. So thirdly, object diagram. So I've shown you a class diagram. Here's an object diagram. This is a variation of a class diagram and uses very similar notation. And the difference being an object diagram shows a number of object instances of classes rather than the classes themselves. And an object diagram is simply an example of a class diagram that shows a snapshot of the system's execution at some given time. Right, so when you've got a working system which uses classes, I mean, maybe you've got maybe the class diagram involves an author class and a computer class, and the intention is that an author can use one or more computers, one or more, between 0 and 1, 0 or 1, 0 and 1 maybe, and the class is named a computer, and maybe it's got the type of computer being used and the size of memory. But I'm going to, in the case where I'm actually got the system up and running, or maybe I'm going to use an object instance of author, which is going to give it a name CK, and Chris, age 30, and he uses work PC, and he's using a compact computer with memory of 64, and he also has a PC, another PC computer, and it's a Dell at a certain number. So maybe, I'm not quite sure where I've drawn all this from. The important thing is to notice that I want to, at one point, analyze the system, and I'm going to come up with a number of classes, and these classes are supposed to give me a way of making transition between the uses of a system and the construction of the system. So the analysis stage is going to result in a number of classes and objects. And I can model the behavior of a particular class. So such a diagram usually complements a class description. A state diagram. A state diagram will complement a class description. And in a state diagram, all possible states of a class are shown, and which events cause the state of the class to change. And a state change is called a state transition, and a transition may have an action associated with it. And state diagrams are not usually drawn for all classes. What I'm thinking about is, or maybe I need to explain the diagram for a lift controller. And what I'm doing is to give a state diagram, a finite state machine in other words, for the lift controller. It specifies what the controller does in every possible event. So for example, if button number 55 is pressed and there's no other work waiting for the lift, the lift controller is going to send the lift hurtling down towards the lift floor, and then on arrival it's going to open its doors, and then after a certain timeout period it's going to close the doors, and so on. So it's going to explain what a particular class is capable of doing, and it might look something like this. So hopefully you can see that. So state diagram for a lift. It might be if the lift is on the first floor, and it might tell the lift to move up one floor. So the state of the lift is that it's actually moving upwards, and it becomes idle when it reaches the floor. It's arrived at the floor, becomes idle. Then maybe the button's pressed when it's in an idle state at a particular floor, and then it's going to move downwards, and so on. So we don't need to investigate that state diagram in any depth, that particular state diagram in any depth. But you can use another kind of diagram to show the collaboration between a number of classes or objects. So, for example, I've got a class. No, I've got an object here called a computer, and it wants to print a file. So, what it might do is to communicate with a printer server, and the printer server is going to send a job to the printer, and then the printer, other things being equal, is going to send the job to, or put it on the queue if the printer's busy, or else it'll actually do the job, and so on and so on. So if the printer's busy, I'm not quite sure what the logic of all this is, but you've got a queue, you've got a printer, actual printer, you've got a printer server. The printer server is going to receive a request. If the printer's free, you're going to print the file. If the printer's busy, it's going to be queued, and presumably there's going to be a communication with the printer server that it's been queued, and the printer server in its own time will actually send the job back to the printer, and so on. So this shows, if you think about it, it shows how four objects, like a queue, a particular printer, server, and a computer actually collaborate to achieve a particular task, to achieve a particular print job task. So anyway, there are sequence collaborations. Here are collaboration. Okay, well, times presented by the vertical axis shows the exchange of messages between objects as time passes. And messages are shown as lines with message arrows between vertical object lines. So just check that out. So time is in this direction. Messages with arrowheads, and so these lines occur in the passage of time, and presumably when a particular print job is done, the printer server will tell the computer that the job has been done. So collaboration diagrams show dynamic collaboration, just like sequence diagrams, but there's no difference in information given. But the latter shows message exchanges and objects and their relationships. But if time or sequence is important to emphasize, sequence diagrams should be chosen. Collaboration diagrams are drawn as object diagrams along with their relationships. So let me give you, I think I've got an example here. So here is a collaboration diagram. Okay, so these are all objects. I've got 5 objects and the user of the system. It's actually the lift system. So I'm pressing a button here. I'm interacting with the system via this a button interface. I've got a button here. That's the interface. That's the only way I can interact with the lift, if you think about it. And then the button sends a message to the lift controller object, and the lift object sends a message to an object called make an order, and this object sends an order for the lift to move to a particular floor, and it's put on a queue. Okay, and the lift, when it wants to, can actually, I think, send a message to the queue. I'm not sure about the direction of this arrow here, but lift can actually ask the queue to give it the next available job for it to do is to move to the floor that this guy is actually waiting at. So what I'm showing you here is what I think is an excellent example of the collaboration between a number of objects that enables part of the, that actually enables part of the use case for a lift system to be realized. I mean, here I'm pressing a button. Oh, hey presto, what happens is that the lift will actually be summoned to the particular floor that this agent is standing on. Activity diagrams. There's a lot of, we've looked at 6 sorts of diagrams so far. Seventhly, activity diagrams. These show a sequential flow of activities. Let me, without any ado, just show you what an activity diagram looks like. No, I can't guess. I'm sorry, I can't actually do it. But the idea is that, this is part of the diagram. Starting here, I think the activity is saving something to disk. There are 2 possibilities: disk full, in which case I'm moving to this, and I'm displaying some message to the effect that the disk is full, and sorry I couldn't save your file, and I finish. Otherwise, the disk isn't full, and I successfully save the file on disk. Let me see. Oh no, something slightly different. I'm actually printing the file, not saving it to disk. I'm going to print the file, and then I finish. Okay, in software you very often see alternatives to the approach that I'm suggesting in general terms here. For example, the waterfall approach, or something called the rapid prototyping methodology, or even agile development. And you might want hardware to do things in hardware. You might want, what's the appropriate design methodology in that case? It's very similar, actually. And it's very important to address, or you may be deemed as adopting an unfathomable, arbitrary approach which will be marked severely. In other words, if you as a designer undertake to design anything, you've got to expressly state how you're doing, what your methodology is, how are you designing it. Okay, so all that was a bit general and slightly waffly, but I'm just going to spend a little bit more time on the same theme. So I'm sorry about this. I've got um, the news being splashed on my recording here, and I can't get rid of it. No, I've got rid of it. So I'm going to. So let me see. I'm going to. So I should really have turned off the BBB recording, which I haven't done. But I'll do that as next thing. Um, oh dear, oh dear. Um, okay, I think something's being uploaded. Nope. Nope, got that wrong. Oh dear, I'm so sorry for this. It's a confusion as to which presentation to give you next. I'm sure I could just give you this. Let me just check this out. Okay, no, this is one I wanted to show. There's a tiny bit of duplication, but that's okay. So, what we've just seen is that the first stage of, I guess, design is object-oriented analysis, and it consists of 3 steps. First is use case modelling. This step determines how the results are computed by the product under analysis without referring to the sequencing of operations, etc. And if you don't like this way of expressing matters, consider use case modelling as simply capturing requirements in terms of the possibilities of interacting with the product. But notice that some ways of interacting with a system are very complex indeed. And we'll return to this first statement again later. So the information is presented in the form of a use case diagram and what are called scenarios, associated scenarios. And a scenario is simply a typical instance of a use case. So this step involves this step involving functional modelling is largely action oriented. So class modelling will determine the classes and their attributes. The interrelationships between the classes is then determined. And the diagram that results is a class diagram, and won't mean very much to you, but it's data oriented. Thirdly, the step of dynamic modelling will determine the actions performed by or to each class or subclass. This information is typically represented by a state diagram, which I've just shown you an example of that. And this step is action oriented. So these steps A, B and C aren't typically performed sequentially. OOA is a modelling technique that simply makes use of the diagrams that the 3 modelling steps produce. Try and remember that. Right. So I'm going to take you through um, a case study. So our first case study is this. This is what I guess is a verbal statement of requirements. It's not a rigorous, abstract representation of the system. I'm just giving you a verbal description. So a product is to be installed to control N elevators or lifts in a building which has M floors. And the problem is to determine the logic required to move lifts between floors. And we have the following constraints. So each lift contains an integral set of M buttons, one for each floor. And the button becomes illuminated when it's pressed and causes the lift to visit the corresponding floor. And the question is, well, how? In what way? What's the scheduling? That's another issue. And the illumination is cancelled when the corresponding floor is visited by the lift. Okay, so pressing a lift, if I press a lift, I'm in the lift, I press the lift button to floor 6. Button number 6 is lit up. When I get to floor 6, the illumination stops. And each floor, except the first and top floor, has 2 buttons used to request an uplift or downlift, obviously. Right, these buttons also illuminate when I press. So if I'm on floor number 99, and I press a downlift, then that button, then that button lights up, and when the lift arrives, the illumination is switched off, and the lift door opens, and so on. And when a lift has no pending requests, in other words, nobody wants to use the lift, it remains on its current floor with its doors closed. And that sounds quite straightforward. So what I'm aiming to do is simply to, excuse me for a moment. So what I'm aiming to do is to create a use case model for this system. So a use case describes the partial functionality of the product and provides a generic description of the system's total intended functionality, and it will be accompanied by scenarios which are particular instances of the use case and represents particular interactions between people interacting, or users of the system, and the specific objects involved in the system. So UML representation of the use case for our case study appears below. It's not terribly complex, and the only interactions possible between a lift and a user is that a user can press a lift button in order to direct a lift, or a user can actually press a floor button to indicate the desired destination floor. And within this generic description, there's a huge multiplicity of possible scenarios, mostly normal, but some abnormal. And I'll give you an example of one um, normal scenario. In other words, a typical use of the system, and one abnormal use of the system, which is very possibly unusual, but we'll see. We'll make a judgment on that a bit later on. But I'm just going to perhaps surprise you by saying, well, I could actually ask you to give me a use case diagram for your use of a doorway. I mean, how can you how can you interact with a door and a doorway? What are the typical uses of you interacting with a door? And what are some abnormal uses of you interacting with a door? I mean, you might think this is a bit stupid, but I'm being deadly serious. I mean, everything I can think of as the potential for my giving it a UML characterization, any functional system I can think of, my motor car, my refrigerator, my electric hub that I'm looking at the moment, which is, I think, I don't know whether you can see that, whether that's in focus or not. Everything's got an associated use case specification for. Well, here it is. This is me, the user, and I can interact with the lift system represented by this rectangle. It's not a class, it's just at the moment it's just the system under description and analysis. What I can do with it is to press a lift button, or I can press a floor button. And obviously I can't I can't press both. Logically I can't press both at the same time. It's one or the other. Either I'm in the lift, in which case I can press a lift button, or I'm not in the lift, in which case logically I could press a floor button because I want to use the lift system. So, okay, so to accompany this use case diagram, I can present a scenario, and it's a normal scenario. So user Chris presses an up floor button, and remember there are M floors, so there are going to be 2M minus 2 floor buttons, and I'm going to press it on level 3 to request a lift, because Chris wishes to go to level 7. So the up floor button becomes illuminated, and a lift will arrive eventually at level 3. But it contains a lady called Luminata who has entered the lift at floor 1 and pressed the lift button for floor 150. So the up floor button is now turned off because the lift has arrived, and the lift doors open, and Chris enters the lift, and then when Chris is in the lift he presses the lift button to request the lift to take him to level 7. The lift doors close as a result, and the lift travels to level 7, and the level 7 lift button is now turned off, and the lift doors open to allow Chris to leave the lift, and then a timer starts giving Chris enough time to leave the lift, and Chris leaves. And the lift doors close after the timeout period, and then the lift goes to level 150 with Illuminata on board. Okay, that's a normal scenario. It helps a designer to understand in some further detail the use case, a typical use of the lift system. And it certainly explains a lot more than just pressing one of two buttons. But here is an abnormal scenario. And firstly, user Chris presses the up floor button on level 3 to request the lift. Uh, because lift Chris wishes to go to level 1. He wants to go down 2 levels. So the up, sorry, it should be the down. I think that's right. So okay, I'm selecting. Oh dear, wait a minute. So I think it's a down button should become illuminated at step 2 there, right? So step 3, a lift arrives eventually at level 3, and it contains Illuminata, who has entered the lift at floor 1, and she pressed the lift button for floor 150. The up floor button is now turned off. So it should be the down button is now turned off. The lift doors open. Chris enters the lift. Chris lift. Chris presses the lift button for level 1. The level 1 lift button is turned on. The lift doors close after a timeout period, but the lift travels to level 150, and when it reaches level 150, the lift button is turned off, and the lift doors open to allow Illuminata to leave the lift. Timer starts, Illuminata leaves, lift doors close after the timeout, and then guess what? The lift goes all the way down to level 1 with Chris on board. And perhaps that's an abnormal use of the system in the sense that you wouldn't expect that to happen. I mean, you might expect the lift, when it reaches level 3, to go back down to level 1 rather than to make a round trip journey of nearly 300 floors. And I hope you agree with that. The point of giving scenarios is that enough information is created in order to give the analyst an insight into the total behaviour of the system being modelled. And the information gained from writing scenarios is used in the next step or phase, class modelling, by helping to determine the class and objects needed to build a system. Right? So we need, as part of the analysis phase, some classes which we'll use to make the transition to building the system. So in this phase, classes and their attributes are extracted, and only attributes are determined. No methods. We're not interested in detail at the moment. The latter will occur during the object-oriented design phase, where you're giving detailed class models. You're giving details to the classes that you arrived in the analysis stage. And following these steps is not a particularly easy task, but the use of objects is very rewarding. So the key question is, how on earth do you guys, potential software engineers, determine the classes needed? So developers will examine the scenarios of both sorts, both abnormal and normal. And if you have a look at the two scenarios above, two possible classes are lift buttons, floor buttons, doors and timers. And we don't want to maximize the number of possible classes. I mean, these seem to be a reasonable but naive, uncritical number of classes that we could use to construct the system. But I want to tell you a bit about the method of noun extraction. In other words, wherever you have a name of a thing, you can initially accept possibly accept that the name of the thing is going to play a role, it's going to have a class to represent it. But we'll see. We'll see that it's a bit overly simple. Okay, for those that don't know anything about lift systems, the above method, this method, could be useful. So stage 1, provide a concise problem definition. Specify the product as briefly as you possibly can and as accurately as can, hopefully within a single sentence. So here we go. What do you think of this? Buttons in lifts and on each level control the position of n lifts, not just one lift, n lifts in a building with m floors. And stage 2 is an informal strategy. You take into consideration the given constraints that I've set out, and there are 3 constraints, I think. Buttons in lifts and at each level control the position of n lifts in a building with m floors. Buttons light up when pressed to request the lift to stop at a given floor. This is cancelled when the request is satisfied. When a lift has no requests, it remains on the current level. Okay, so a formal strategy is that in this you identify the nouns, excluding those that don't actually form part of the problem itself. You underline the nouns in the informal strategy. So you underline buttons, lifts, level, position, lifts, buttons, building, request, lift, give level, request, lift, requests, doors, and so on. So you've got 8 nouns underlined. So these are the 8. And they're provisionally extracted. But building, door and level aren't really within the scope of the system problem, the boundary problem. I mean, let me see. The building itself, it's got nothing to do with the lift system. Doors aren't incredibly important, and levels aren't really part of the problem as such. So we can sort of reflect on that. So position and request and illumination are abstract nouns, and it's likely that they're good candidates for classes in the form of attributes. You know, you can talk about a button being lit up, a button being illuminated. So sieving through all that, it just leaves 2 candidates, elevator and button. But there are 2 types of button, aren't there? Elevator or lift and button. It's all that's really strictly relevant. And there are 2 types of buttons spoken about. There's a floor button and a lift button. So maybe as a first attempt we've got a button, and they've got subclasses, a lift button and a floor button. That's the superclasses, one general type of button. And you've got a lift. So we've got n lifts, and each lift communicates. You can communicate with a lift button, and you've got 2 m-2 floor buttons, and the lift can actually communicate in some sense with the floor button. Therefore there are at least 2 base classes: lift with attributes doors open, doors closed, and button with one attribute lit up, not lit up, and the arrows indicate the subclasses of button. It's not a particularly good start, however, because surely buttons don't directly communicate with the lift. I mean, if I press a button, it's not actually talking to the lift itself. What it will be talking to is the controller, lift controller. Okay, so I don't know what you make of all that. You probably think this is rather silly nonsense. But as I said, the idea of actually representing the requirements of a system is very, very important. And the way of actually graphically illustrating how somebody can interact with a system's pretty important. And what we've seen is that a use case diagram has to be associated with scenarios. You have to explain the nature of the interaction. That's important. And when you do that, so I'm actually just going to, perhaps I should stop the recording here. So I'm stopping the recording. Yeah, so I'm going to pause the recording. It's gone over an hour, so I probably won't get a recording for BBB. But once we've got a summary specification of requirements, we can actually think very carefully about, well, what are the key objects, what are the key classes that we need to use in order to model a system in such a way that we can actually realize these requirements, and that's the important thing here. So I'm just going to move on. I'm sorry but time is running out. I'm going to get rid of that, and I mean, after I've shown you the next little presentation, I am, oh crikey, 1, 2, 3, 2. The next time, the next, in the next part of the overall work we're doing this afternoon, I'm going to show you a video clip and discuss that a little while. So, anyway, got that wrong. So, if you remember, a few minutes ago, we arrived at a provisional class diagram, and we need to reconsider it because we need to include a controller, and we can, if we needed to, we can actually talk about, for each class that we have in the system, we can actually talk about a CRC card, which is simply a very simple representation of the class by specifying its name, saying what its responsibilities are, and to specify with what other objects or classes it collaborates with. Okay, and that's going to help us with the next stage of design. So what I'd like you to do at some point, if you're a very keen and energetic student is to look up or Google CRC cards, and it stands for Class Responsibility Collaboration Cards. Just simple descriptions of classes and their given responsibilities and their given collaboration. Remember, uh, to make a system fully functional, after you've split it up into several classes, you've got to state how those classes interact with one another to bring about overall system functionality. Right. So please do a little bit of research what these are and how they're used. Look at their typical use. And we then looked at a state diagram for a lift controller in a very short terms. So when we've done all that, the object-oriented phase appears to be complete apart from a final review, a final critical commentary. So let's just spend a few minutes looking at what we've done. Um, if you think about a lift controller, presumably amongst its responsibilities are the responsibility to open and close the lift doors. But surely the lift controller isn't itself responsible for these actions. All that the controller should be doing is to issue messages at the right time, in the right state, to the devices it's controlling. It'll tell the lights to switch themselves off. It'll tell the door to open or to close. It'll monitor um, a timeout timer, and it'll close the door after the timeout period has elapsed. So as far as opening a lift door, surely in the object-oriented world, this should be replaced by something like send a message to the lift door telling it to open itself. In other words, I'm assuming that the lift door is going to have a method which I can invoke, and the method is going to close or open the door. That's fine. I'm sending it a message. And what I mean by that, in fact, is executing the method to do that. In a well-designed system, operations are packaged together with the data the operations are operating on. And that's the heart of object-oriented programming, after all. We know that a class's data members represent state, and it doesn't take very much reflection to arrive at the conclusion that a door has state. Okay, so I'm thinking, let's just backtrack a little. I'm thinking about a class representing a door. And, in fact, I'm thinking about instances of that class, objects, door objects. Door objects have state. What do I mean by that? Well, they're either open or closed. So we can... so what's this? So from this we can infer that we should represent a door by a class. Yeah, that's okay. And this is what's missing from our state diagram. Is it? I'm not sure. Let's have a look. So everything makes better sense. It's the responsibility of the controller to send a message to a lift object telling it to open or close its door at the right time. Yeah. The object will contain a method, yes, open, that changes its own state from close to open. You should now start to think about supplying state diagrams for each of the classes that have been derived, including the door class. In addition, we should rewrite the collaboration responsibility cards to reflect the fact that we're actually now thinking about OO analysis. In other words, we're sending messages. So the class diagram looks like this. And a generic button class. We've got subclasses elevator button, floor button, elevator controller. We've got doors and the elevator itself. So the elevator is going to be controlled, or the lift is going to be controlled by the controller, and the controller is going to do, in response to messages sent to it via the buttons, for performing the appropriate tasks at the right time. So it can do things like open the doors, close the doors, move down, move up. And given the fact that we've spent time developing a range of diagrams for the system, it's not surprising that the range of case tools. Okay, so we've done some analysis. Let's just, I mean, you might not think this is wonderful stuff, but what we've got here, what I'm showing you here, is a collection of classes, or if you prefer, objects, because after all, I've got an elevator class here. Sorry, I've got an elevator. Let me start again. I've got an elevator class here, and I've got n of them. I've got n lifts, in other words. And I think they're all going to communicate with one and the same controller. And the controller is actually going to control m elevator buttons in each lift and 2m minus 2 buttons on each of the m floors. Okay, so we've made a little bit of progress, and we're moving to the design phase. And for each class diagram, we've got to specify interaction diagrams for the scenarios that we've considered. We need to construct a detailed class diagram, which means we've got to specify all the methods that each object has. And then we've got to design the product in terms of the clients, right? And we need to proceed to the detailed design. So step one, interaction designs. We want to specify how the classes interact with one another. And we've seen that UML supports two types of interaction diagrams: sequence diagrams and collaboration diagrams. And I'm showing you examples of each. And in the case of sequence and collaboration diagrams, both kinds of diagrams show exactly the same information, but with different emphases. Sequence diagrams focus on timing aspects. Collaboration diagrams emphasize the relationship between objects, and are useful for understanding the structure of the system that we're making. So guys, look, this is a system. We've got these classes or objects. We've got the user, we've got the floor button, lift button, we've got the controller, we've got the lift itself, and we've got the doors. So Chris Kernberg comes along. So time is represented in the vertical axis. At this point in time, Chris Kernberg presses a floor button, and well, what happens to it? I don't know what's going on here. I think the floor button should actually be sent. So I can't change this, but I'll do it in the final day. If I press the floor button is actually going to communicate with the controller, and in response, at a shortly later period of time, the controller is going to send a message to the floor button to turn on the light. And as a result, okay, so the controller's got some work to do, and it's going to tell the lift to move up, possibly 1 floor or 10 floors or whatever. and the lift can actually report on which floor it's at the current time, and the controller can say, okay, you've reached your destination target, and now I'm going to turn off. This is a bit strange actually. Here I pressed the floor button, so this message is just going to the floor button. Here the lift is telling the floor button to turn off its light. It's arrived at its destination, and at this point in time the controller is actually going to send a message to the doors saying open up, open the doors, and at point 6 Chris Kinberg presses the lift button. Well, forget that, because the message, if I was pressing the lift button would go to this point. Am I reusing the lift? Here I'm pressing a floor button, so I'm actually in the lift, and I'm going to a particular floor, and then I open the doors and get out. Maybe at time 6 I'm pressing a lift button again, but this message should just go to this object here. This object here. It's a sequence diagram, part of the sequence diagram for the lift controller. It shows what the system should do on a pair object, on a pair class basis. It's showing the sequence of messages that pass between all the objects in order to achieve the overall behaviour that I want from the lift system. That much is clear, I think. Okay, so I'll leave it at that. I'm not going to ask you to do what in effect is another significant piece of work. I'm not asking you to do that. I'll leave you with things as they are, and I'm hoping, so I'm recording, on my recording I'm recording international news, just ignore that. So what I'd quite like to do is to show you a short video clip, and I don't think I've actually got, I'm going to have to share my screen, and the danger of doing that is that when I've shown you the video I might not be able to get back, so you expect me to have to log back in again. Okay, so what I'm just going to fiddle about a little bit, and going to this is going to take 3 or 4 minutes to set up, so if you want to just relax, if you're not relaxed already, if you're not asleep already. Right. So I'm actually going to set up Eclipse. I'm still here, but I'm just trying to get something running in the background so I can show you by sharing my screen with you. Right, so I'm assuming you can actually see one program in Eclipse at the moment, and it's called Client, UDP Client. And what I'm going to do, I hope you can see this. What I'm going to do here is to run it, and I want you to see what happens. So it's telling me what my IP address is, and what I can do here is to send it a message, and I'm going to type just hello in green, so I hope you can see hello, and I'm going to press return, and okay, that's great, and nothing's happening. Right, so so I'm determined that this I can get this to work, so I'm going to restart that by clicking on restart, and I might abandon this if it doesn't work. It's a shame, but I do actually have um, a video clip which I'll put onto Pharos later. I'm showing a server and a client, It's taking ages. Um, to actually. Okay, so I'll just try again. So I'm going to try running the server again, and I'm going to type hello again and see what happens. So nothing happens. Um, okay, last few minutes. I'm just going to try one more thing. Going to try restarting the server. Okay, I'm going to be away for about 3 minutes, and I'm going to probably abandon this. But what I want to do is to actually show you the coursework I'm expecting you to do in a moment. So hang around, please. So it's just, I think my PC's just really overloaded at the moment with lots of things running on it. So what I'm going to do, I'll put the video I wanted to show you up on Pharos, as I said, and we'll do a little bit of work on streams on threads next week. But what I want to do is to end up showing you the first version of the coursework that I want you to do. And as I said, for those that weren't actually here at the beginning, I'm setting it at the end of next week. And so what I want you to do is to submit it 2 weeks after the end of your exam period. Okay. So let me just get all this. Let me just show you the document I wanted to show you. I hadn't realised time had passed so quickly. This time I got myself a new laptop, I think. So this is the assessment coming up. So 5 questions, and 3 of the questions will be done by the newcomers. All 5 questions will be done by January starters. And the questions are how is a TCP segment defined, how large can it be, and how can you actually determine the size from the fields contained within the segment? What mechanism is available for TCP to fragment segments? Show by using a diagram how this is possible and how reassembly takes place. So that's quite straightforward. If you were present, you should have a clear idea and you know where to look and how to answer that. Secondly, how do sliding windows provide a method for implementing flow control? Which I think is a very important topic, but it's quite straightforward. Start by explaining the importance of such control. Why do we need flow control? And this is all TCP again. Illustrate the sliding of a window to achieve flow control. What factor determines the distance a window can move or travel, and at what point will it move? Well, it's to do with the receipt of acknowledgements. Third question. Another way by means of which flow can be controlled is via the use of a congestion window size, determined by a TCP strategy and policies appropriate to the events determined. And I'll make that a little bit clearer. Secondly, so I'm not asking actually any question. So I should really say, explain the use of congestion window size. Oh no, perhaps this is part of the question. Draw a diagram showing the beginning of slow start phase when RWND is assumed relative to a low value of congestion window and the SS threshold is set to 32. Explain what happens when congestion window reaches the value of SS thresh, and now suppose etc, etc. So the little problem here, and I just want you to give me a detailed diagram. That's question 3. Another way by means of which flow can be controlled is by means of the use of congestion window size. So the question actually asks you to, nothing in A, but it's B, just draw the diagram. What happens? Illustrate that happening. Fourthly, what's meant by UML, and explain to what modelling uses it can be put, and give an example of say a lift and how the lift's behaviour can be modelled using UML. Give relevant examples of classes for the analysis and design of a lift system. I'll give you a bit more detail and we'll talk about that a little bit next week. Question 5. Explain one essential feature of making a protocol reliable based on the work you did last term. Well, obviously, Mohammed won't be able to, or might find it difficult to do. So I'm not asking him to do that. I'll select three other questions. Do 2 questions out of 5, and the people that join the course late. Right. So question 5 is explain how stop and wait protocol could be based on the use of UDP, and you may take a pre-written client-server pair of programs to explain the operation of each line by line. Well, the work that we did last term was that if I send you a packet, what I need from you is an acknowledgement, and it's only when I receive an acknowledgement will I send you the next packet, and so on. Okay, so for January starters, I think you'll be able to very easily do all that. You'll be able to find your way around, and you've got something like 4 weeks from now to do all that. But I do need, I need submission 2 weeks after the exams, and I'll select 2 of these questions out of the 5 for the latecomers to do, because the latecomers will still have lectures after, I think it's after the exam period, and I think you've got 3 weeks worth, and we'll do a second assessment at that point. So thank you very much for your uh, uh, support and continued attendance this afternoon, in spite of the local problems I've had with showing you something I wanted to show you. But I shall put the little video clip up, and I shall give you a few notes for you to look at. Okay, so Mohammed and Mustafa, there's no Ikram here, unfortunately. But thank you all very much for attending. And if you have any questions, do let me know. Raghead, if you want to talk to me about anything, please do. Same for Mohammed and Mustafa. Okay, so I'll say goodbye because I'm 10 minutes over the allocated time. And see you next week. Mustafa, hi. Thank you. Ragad, thank you. Mohammed, thank you. And all of you have a good, happy, safe, enjoyable week and work hard for your exams. Okay, bye bye.